A lot of times you would do a board, right? So you're complete, you're ready to go to the market, you're testing the board, and you have made a mistake. Right? This is all about fixing that mistake, accepting the mistake and fixing it up with the glue logic. So looking at the design challenges of logic, as I said, day in, day out, we hear that. Okay, my design is perfect, my board is ready to be shipped. Oops, there's just one gate missing outside the microcontroller. Oops, if I could just invert the data signal going into the controller, right? Or if I could just multiplex the output for the memories. This is what the logic does, and this is where it comes into play. But whoever does this is considered to be, oh, okay, he's a bad designer, right? Logic should never be used. It's a cost adder. Why would I ever use a logic? So these are all the myths and perceptions. So what are the facts? Logic is everywhere. So last year, the total market for logic was about 20 billion units. NXP ended up shipping about 7 billion of those units. This makes us the largest volume suppliers for the standard logic. We have about 30% of market share, and it's growing. So looking at the state of embedded systems, how it was done in the past, right? So the systems were bigger, there was no power constraints, you could consume pretty much triple or 4 times more power than what you do today. They were not as much portable. A lot of core functions like multiplication, adders, subtraction, EPROMs, IOs, they were done with the logic, right? So you would use a lot of AND gates, NAND gates or OR gates to build those functions up. And that was the state of logic like a few decades ago. The systems were bigger, the packages were bigger, and then most of the popular packages were even DIP, TSSOPs and SOs. And as I said, the standard logic offered was in quads, so you would find 4 functions, 6, maybe 8 in one package, right? We would be addressing the design issues like signal integrity, PCB routing, in addition to the core functions that were done by logic at that time. So popular functions back then was buffers, level shifters, and some simple decision making like control and reset functions. That is still not changed as of today. So today's embedded systems, they are smaller, they are portable. There's a lot of pressure to keep the battery budget in check, and you would like to maximize the battery budget. The PCBs are also becoming smaller, right? And the space is also becoming more critical. So that is where the logic is also evolving. Some more trends that we see are RTOS and software is becoming more critical. There's more interaction between hardware and software today. What does a user expect out of all this? And the user's expectation from today's embedded systems is, for sure, he expects a longer battery life. He needs some cool features like touch screens. He needs the stylish designs, thinner, smaller systems. He wants new features in every release. The reliability is expected out of that, the robust, high-quality operations, and all that. So in this session, we'll see how logic gets you to the market quickly, and how logic gets these embedded systems to the market quickly without respinning the ASIC or without respinning your microcontrollers there. So a bit of history about embedded systems. In the 70s, we had bigger boards. The popular packages were DIP. The trend continues into 80s, where you would see the SO, SSOPs. Boards became slightly smaller. In 1990s, the trend continues. TSSOP dominates. And these are like 16 pen or more packages on the board. So coming into 2000, the trend continues. You see more and more size shrinking, smaller systems there. The popular packages are becoming leadless packages, which are QFNs, thinner packages. And this is what we see in smartphones today. And going into the future with smart wearables, as well as integrated phones, wireless charging, what's going to happen to the ICs and logic in particular? I mean, that's a question to us. And we expect even more smaller packages, maybe flexible packages for the embedded systems. So looking at the standard logic, today it's gluing the different interfaces like memories and MCUs together. There are some additional gates outside the microcontrollers for quick reconfiguration. It's still improving the signal integrity and signal quality. It also does some ESD protection. on the boards, multiplexes, shifts, or latches the signals, and sometimes we do extend the GPIOs and drive the LEDs with them. So the standard logic has evolved in the last few decades from bigger packages and more functions in one package, like they used to be octals, quads, and hex, and it has evolved into smaller single, dual, and triple gate functions. In terms of packages, you would see the trend going into leadless. Even the latest package is the diamond package, which measures 0.64 square millimeters. That's small. But again, here you had 4, 6, or 8 functions. Here you are looking at single, dual, and triple gates. Another trend is to keep the bigger pin count packages and more functions still on a single package, but move into QFNs. This is again the leadless packages with a bigger pitch and thinner in terms of height. If we look at NXP's portfolio and features, we have logic families for pretty much all the popular nodes in the system. So we go up to 15 volts. We have solutions for 5 volts, and we operate down to 0.8 volts. So these are all different logic families, and we'll look at what makes them so different and why do we need so many different families, and what are some of the features there. So when it comes to the portfolio, there are gates, flip-flops, configurable logic, combination logic, still counters, shift registers, buffers, line drivers, etc. in the portfolio. If you look at the different families available, the families in green are high voltage families. So they go from 5 volts up to 15 volts. And the total number of functions is on the vertical scale here, with the operating voltage here on the x-axis. You will see most of the functions in HCT logic. This is our traditional 5 volt logic, mostly used in automotives, industrial systems. There's a TTL compatible version of that with HCT. And then as an example, in the low voltage families, LVC is still very popular. So we are shipping a lot of LVCs. This is a 3 volt family, and you can see about 150 different unique functions are available in LVC. This is a chart which shows the operating voltages for these families. Again, as I mentioned, the high voltage families like HEF operate up to 15 volts. Then we have low voltage families. The latest one of them is AXP, which is the lowest power and lowest operating voltage family. It operates down to 0.8 volts and consumes the lowest power. Looking at the drive current, you would need different output drive currents, which is the sink and source current, depending on your application. Most of the high voltage families have the stronger output drive. For example, LVT is a bi-CMOS family. You can sink or source up to 64 milliamps out of LVT. It's more suitable for switching applications, like telecom switches, base stations, backplane applications. And then you would expect lower output drive for low voltage and low power families, like AUP, AVC, and LVC, which are pretty much there in the logic families for about 20 to 25 years. Our latest logic family is AXP, as I mentioned. We launched this like 6 months ago. The output drive is limited up to 4 milliamps, but it operates down to 0.8 volts. So it's more suitable for newer applications, portable applications like smartphones, tablets, etc. And then if you look at the propagation delays or speeds, you would see lower propagation delays or higher speeds for low voltage families, which are in blue here. And as you go higher in the operating voltage, your propagation delay also increases. So these families become slower at higher supply voltage by design. And then looking at AXP, our objective was to offer a family which has an optimal balance of operating voltage and propagation delay. So it fits right between AUP and HC, between 3 and 5 volt families in terms of prop delay, but still gives you a supply voltage down to 0.75. So if you look at the life cycle of these logic families, you would see most of the newer logic families on the left-hand side. These are kind of in the ramp-up or introduction phase. You would see AXP, AUP, and AVC. Those are the low voltage families. Most of the 5 volt families, including LVT and HC, they are kind of mature, and they are shipping in volume there. but then the bipolar and bi-CMOS families are on the right-hand side, which are in a declining phase or being phased out. So looking at the different features of these logic devices and electrical properties, in the data sheets you can find some features like power off leakage current, oversupply voltage tolerance, low to high and high to low voltage level translation, the TTL compatible inputs, power up in 3 states, etc. All of these features will help you fix a specific issue on a board in your application space. So we'll be looking at some of those features and how do they help. So power off leakage current is specified as I off in the data sheets. So this makes these devices suitable for standby modes or power down modes. So the idea is when your logic device is powered off, you would like to make sure there is no current coming in from the receiver side. So there is no backdrive for the device which could destroy the outputs of the logic device. And this is specified in the data sheets as I off, and it's up to nanoamps or microamp, 1 microamp at most. Another thing is the over voltage protection. So we have designed the inputs and outputs of these logic devices to tolerate the supply voltages, tolerate the voltages higher than supply voltage. For example, at the input of logic device, you could supply a voltage or apply a signal which is higher than supply by 0.7 volts, right? And you would eliminate any path going to the supply voltage. So in that way, you're protecting the device for oversupply voltage. Same is the case at the output. We have a comparator designed in at the output, which looks at the signal and decides if it's higher than the supply voltage, it eliminates any path or the current going to the supply. The outputs of these devices, they are held in high impedance during power up. So the idea is when your supply voltage is ramping up, you would like to make sure there is no sink or source current going at the outputs. So in that case, you would make sure there is no glitch at the output during power up until your supply voltage becomes steady. This feature is specified in the data sheets as IOZPD, which is power down 3-state current at output, or IOZPU, which is power up 3-state current at the outputs. So by specifying that, we are making sure the device is suitable for standby or live insertion capable applications without being damaged. Looking at the voltage level translation, you can do a low to high or a high to low voltage level translation with logic devices. So the idea is, since the inputs are oversupply voltage tolerant, you can supply a signal which swings above the supply voltage, but then your output will always swing up to supply voltage. So you can do a simple high to low level translation with logic. Some of these devices have low CMOS input thresholds. So what that means is the device will trigger with the signal which is lower than typical CMOS thresholds, but then your output will always swing to supply voltage. Same is the case with the TTL inputs. The devices with the T in there are TTL variants. So they will switch at the 2 volts for high and 0.8 volts for low. So that can also be used for low to high level translation. In addition to that, in our portfolio, we also have dual supply level shifters, which are ground up level shifters designed for this specific purpose. They will have 2 supplies, VCC A and VCC B in there. And this chart shows you the input thresholds, both high and low, for different supply voltages, and also the expected output levels, both low and high at the outputs, at these supply voltages. Another important feature is the bus hold. Let's say in your design you're using a 16-channel transceiver, right? And you would end up using only 13 channels of that. So the remaining 3 channels are floating on the board, and in a typical CMOS design, you would like to make sure the channels are not floating, the pins are not floating, because then you can have some oscillations on the board. What bus hold does is, by default, it pulls them up or pulls them low, so that there are no floating pins on the board. It saves you some PCB space. It also saves total solution cost. It can also be used to hold the last known state of the inputs. And the idea is you would need to drive the inputs with larger current or more current if you want to change the state. And that current is specified as here, IBHHO in the data sheet, up to 500 microamps. Bus hold does not guarantee that when your device comes up, the inputs will be pulled up or pulled low. But if you want to make sure those inputs are always pulled up, you can calculate a pull-up resistor and use it in your design here with the bus hold inputs. And then some of these logic families, they also have Schmitt Trigger inputs. What that means is we have two different switching thresholds in the design, one for going from low to high and one for high to low, and nothing happens in between. So your outputs will not toggle if your signal level is in between the two thresholds, which is called hysteresis zone, and that's what we are showing here. Schmitt Trigger can be helpful in a noisy environment where there's a tendency to have a signal in the hysteresis zone, and you would still like the outputs to be defined. So that's where logic families with the Schmitt Trigger can be used. So looking at the common application issues, again, all of these things can be done by logic and still are done. For example, we improve the signal integrity, we do some level translation, we latch the signals, we do the left to right shift or right to left shift with logic. But let's look at some of them. So in a microcontroller, you would have different I/O voltages at the pins, and when you are interfacing with peripherals like memory, like RAMs or LCDs, you would need to go between one voltage and the other voltage, specifically if they are operating at two different voltages. This is where our dual supply level shifters come into play. We have two supply voltages, VCC A and VCC B, and you could pretty much go between this and this voltage depending on if your microcontroller needs to translate or send out a signal at one voltage, but your peripheral is at the other voltage. There are different families, AUP being the lowest power level shifter. LVC gives you more output drive, but is up to 5 volts. And then we also have AVC, which is here. And then these devices are available in 2, 4, 8, or 16 channels, depending on how many channels needs the level shifting. In addition to level shifting, for example, in your design, if you're missing one GPIO, you need 8 to access the memory, but you only have 7 coming out of the microcontroller. You could put a 1 to 2 demultiplexer and get one more line accessing the memory, and this is also a glue in your design there. Looking at some more examples, let's say you have a clock and data coming from your ASIC, which needs to go to a different ASIC out there. But once you're done with the design, you realize you need the inverted signals. You need to invert the clock, and you need to invert the data, and you also need to latch it up. We have solutions which are standard logic, like a flip-flop here and a NAND gate here, which can be used for the clock and data. You can fix both and then drive it up to your ASIC here. So in the past, this was done with the standard solutions, which were higher pin count. Even though if you had to use a couple of channels there, you would end up getting the whole package, and that would take a lot of space, and the layout will look out messy. So today, we offer the solutions which are 6 lead, up to 6 lead. Again, those are single, dual, and triple gates. You can do a clean routing, save some PCB space there, and it optimizes the whole board. Some more examples. You can implement a Pierce oscillator using an unbuffered inverter. You can convert a synchronous reset signal into an asynchronous local reset using a flip-flop. Using a Schmitt trigger, an RC oscillator can be built. And then we use the shift and storage registers to drive the LEDs. So the idea is you can cascade these shift registers and drive the LEDs if you're running out of IOs on a microcontroller. This is the common application of shift registers even today. Saves you some pins on the microcontroller. Some more examples, if you want to make a clock divider, can be done with the flip-flop and inverter. Switch debouncing can be implemented with the Schmitt Trigger. You can drive the LEDs by using a pull-up on an open drain output. So in that case, when your buffer is at low output level, the current will flow from external supply into the buffer, which is here. And you can increase the drive capability, also do some level shifting, depending on what your external supply looks like. So to drive the LEDs, this can be done with the serial to parallel data conversion. Again, these are the serial to parallel converters with shift and store registers. When the outputs are low, the current will flow into the device, and you can drive the LEDs there, typically 20 milliamps each. And you could be sending the data from your remote processor and also the clock in there. So the requirements of today's embedded systems, we need compact, smaller designs. We need longer battery life. We need to get these systems to the market quickly. They have to be high quality, high reliability, robust. We need to save some space. And then at the end, you need to get them to the market fast. So you need to be flexible with that. So we address the need for low power consumption with our low power and low voltage logic families. So we have 3 different families: LVCs, AUP, and AXP logic for this purpose. We combine several different functions into combination and configurable logic. So we'll see how you can have multiple functions in one package and then can configure it on the board layout at runtime. We are innovating a lot of packages for logic also, mostly in the leadless space. So that also helps to get to the smaller size. So when it comes to the AXP logic, this is our latest and lowest power consumption family in the portfolio. As I mentioned, it operates down to 0.7 volts. It's fully compliant to the JEDEC levels. The static current you would see is up to 0.3 microamps. When the device is switching, that's your dynamic power consumption. It only consumes up to 3 picofarad during the switching. Prop delay up to 2.5 nanoseconds. There are Schmitt triggers at the inputs. And the first device that we did in this space is the configurable logic. So later on, we'll see how you can configure one device into any of 7 unique functions, and that's what the configurable logic is. Like other logic families, AXP logic is automotive qualified. So that means we operate up to 85 degrees Celsius by design, and you don't pay the premium for that. Looking at the power consumption numbers, as I mentioned, there are 2 major contributors for power consumption. One is the static power consumption, and second is the dynamic when the device is switching. So we looked at the AND gate, the 2-input AND gate, and the numbers for static and dynamic power consumption. So LVC logic, which is the highest runner, low voltage family in the industry, consumes up to 33 times more static power than AXP. So that's how much of a power you can save when the device is static and not doing anything in your system. Looking at the dynamic power, LVC consumes up to 4.5 times more power than AXP, and these are the numbers at 1 megahertz. So by using this AXP logic, you can save that much power during switching, like 4.5 times less. And these are the numbers when supply voltage node is 1.2 volts. Here's a graphical representation of what we said. If we look at the low voltage families in the portfolios, like AUC, AXP, AUP, you could see AXP has a dynamic power consumption less than 5 picofarad, and then a prop delay of about 5 nanoseconds. And it also operates below 1.2 volts. So again, the message here is there's an optimal balance of propagation delay below 1 volt, and we have also minimized the switching power consumption for that operation. So looking at the integration of logic functions, there's a combination logic, and the idea is you can combine 2 or more functions which could be different. or which could be unique in one package. Typically, those packages are 6 to 8 leads, and those functions could be separate in a package, or they could be connected, like this one. So the nomenclature for these devices is when there are two unique functions which are not connected inside the package, you would see as 2G in the part number. And if those functions are connected together, you will see 1G. Like we have a function which is AUP1G0832. You have 3 inputs, and an AND gate and an OR gate are connected together. Right? So your output is a set of specific Boolean function, but you have more than one function in there. And this is how it works. Let's say you have two different devices and packages. You want to combine them both. Now you have the same function in one device. You save up to 50% of space and cost. So moving on to configurable logic, the idea is we have many gates in one function or one package that can be configured into a unique function. That is different from combination logic. You can define a function during the board layout. Once the board is laid out, the device is configured into a specific function. It cannot be changed. That is how it's different from an FPGA or a software-based configuration, which is also available in the market. Up to 9 different functions can be configured out of one device. Some of the standard function examples are AND gates, OR gates, NAND, and buffer. Again, this is the same device, but all of these functions can be configured out of that one device. And later on, we'll see how that works. And then there are some non-standard functions also, which are available in that package. So what are the advantages? Why would you look at the configurable logic? It gives you the flexibility, because now you don't need to build an inventory of 9 different functions. You can do that all with one device. There's a cost savings, again, by inventory management. There are some space savings also. And then there's improved system performance, because when we connect these gates inside the package, there's an improvement on electrical properties like propagation delay, etc. So this is how you would configure them on the board. Let's just pick 2 examples. This is your 6-lead device. By connecting pin 1, 2, and 6 to ground, you would get a single channel buffer with 1 input and 1 output. And this is done when you are doing your board. Same device, if you connect pin 1 and 2 to ground, but then leave pin 3 and 6, they become the inputs of OR gate, and the same device becomes a 2-input OR gate. Once that is done, cannot be changed unless you're doing a new board. These are all different functions, an eye chart of what's available out of 1G57 function. We have 4 different types of configurable logic functions: 57, 58, 97, and 98. This one shows you the available functions in 57. And then there are variants of these devices with integrated level shifting. So some of these functions will have low input CMOS thresholds, so that you could still do the low to high level shifting and the desired Boolean function as you would need. So this is a table of what's available as standard functions. For example, in a 57 part type, you will get AND gate, buffer, inverter, mux, all the green columns as your standard functions. And then there are some non-standard functions also. As I mentioned earlier, these configurable logic devices can also give you a non-standard function like an AND gate with an inverter. This is how you would space an extra inverter in your design if you needed an inverted input for your AND gate. So better performance than individual gates. Again, for the same reasons, you get some improvement on the propagation delay when you go from input to the output. Again, the size is also smaller if you look at the overall board. So here's the propagation delay improvement. Instead of 5 nanoseconds, you are looking at 2.9 nanoseconds combined. And this table gives you the non-standard options or non-standard functions coming out of each of these devices. For example, in a 97 function, you could get an AND gate with 1 inverted input, or a NAND gate with both inverted inputs, etc. So all yellow columns are non-standard functions available in configurable logic. So if you look at the computing platforms today, like tablet PCs, like some of the Chromebooks, for example, this is where you would see the typical use of these logic devices. So the single gate, dual gate, and triple gate logic, you would see it in the battery charging, where you need some overvoltage tolerance and high output drives. You would see some CBT switches, which are also logic. These are the crossbar switches. You could do some graphics between displays, graphic switching between displays using crossbar switches. And some of the test interfaces like JTAG and reset blocks, we find the dual gates like AUP logic. Again, these are noisy signals. You want to make sure your output is well defined. So sometimes you would put in a Schmitt trigger just to get a defined output there. If you look at the mobile phones, tablets, and cameras, again, this summarizes the use of glue logic and interfaces like baseband and RF. We also find them in baseband reset blocks. And sometimes there's a level shifter between baseband and memory. So the important thing to note here is the supply voltage is going low and low. It's at 1.2 volts or 1.8 volts today, but we have seen some processes going down to 0.8 volts, and the trend is to use 6 or 8 lead glue logic devices rather than the bigger 12, 16, or 14 lead devices. So some real examples coming out of schematics. We'll go through them quickly. Sometimes when single channel buffers are used in the audio control interface, again, the idea is to buffer some of the clock, sync, and data signals. These are low frequency interfaces, typically up to 50 megahertz or so. In the tablet PCs or so, you will see the AND gates being used to extend the low pin count interface at the docking side. And it also combines and buffers the signals like interrupts, data, power down, and reset lines to improve the signal integrity and signal quality on the board. In the battery charging interface, we have seen the NOR, AND, and exclusive OR gates. They are used in the charging and management circuits to monitor the voltage levels. So in short, these gates would generate the interrupts for the controllers if your battery voltage goes below a certain threshold or above a certain threshold. So a cheap and easier way to implement the power management controllers to signal the battery levels. And here's an example of scan matrix keyboard interface. Again, these are the CBT-D switches. The CBT-D switches have an integrated diode between the supply voltage and output enabled control. They are used for level shifting from 5 volts down to 3.3 volts. And there's a low voltage version of that, which goes from 3 volts to 1.8 volts. In a scan matrix, these are, again, the clock and data signals. You have 5 volts coming in from the driver side. Let's say you want to isolate the interface, get 3 volts here. You can use a CBT-D switch. Looking at the logic packaging portfolio, just an eye chart here. The leadless packages, leadless smaller packages are on the left-hand side, on the ramp side. They are still gaining popularity. They are in introduction phase. The latest package is a diamond package. This is the smallest package available for logic today. Only measures about 0.64 square millimeters with 0.5 millimeters pitch. And then on the trend, you would see the dip packages on the right-hand side, which are being phased out or in discontinuation phase. So if you look at the packaging evolution, this is a dip package. Probably before I was born there, like 40 years ago. The top row has evolved into smaller leadless packages, but they are more than 4 or 5 functions in one device. Right? So the trend is to go leadless, and today it's at BGA or QFNs. Here is where most of the volume is today, all the single, dual, and triple gates. And you can see the smallest package, which you just saw, is 0.64 square millimeters, but still with a pitch of 0.5 millimeters. Again, one of the advantages of this package is, in the manufacturing environment, when the package size becomes small, your pitch is also reduced. And you need a step-down mask to put it on the board. And that increases your cost. With this package, your pitch is still 0.5 millimeters, and your stencil cost is not that high. So in the final section, we'll look at the design and demo tools. Since these packages are becoming so small, we have some converter boards available. The idea of these converter boards is they will convert the leadless packages into DIP packages, mainly for evaluation and benchmarking, so that you could look at the timing properties, the static and dynamic characteristics of these devices. So only one package can be mounted on the board at one time. So we have the footprints for all these packages, but you can only mount one device at a time. And we have 4 different types which can accommodate up to 37 different packages on the board. We also have an evaluation board. This evaluation board lets you look at the input and output signals of a configurable device. At the same time, each of these sections can be configured into a unique function. By defining the inputs and outputs, these boards can backdrive the next stage too. So you could backdrive this device from this. You could supply one voltage for all 4 sections, or you could snap them off and use them separately. The same board is available for different logic families like LVC and AUP as well. We are also running a design contest where we are giving away these boards to a lot of designers who are using these boards to come up with unique applications by configuring the device into any of those functions. And then we have a demonstration board also that gives you an idea of how this configurable logic works. So there's a selector switch on the board that you can use to select a function, and then there are some push buttons that can be used to give the inputs, and then LED tells you the status of that device or the outcome of that device. So there is a sample kit which comes with a board. There are some actual samples in there, some printed brochures, and a USB stick. This kit is available from local sales if you're interested. And then the takeaway messages. NXP has a huge portfolio of logic functions. If you look at the portfolio, we are the largest, even bigger than TI, for both standard and glue logic devices. With AXP logic, we have the lowest power consumption family. We continue to invest in innovation, including the functions as well as the packages. Our quality and supply chain is best in class because we are in automotive. So we are the largest supplier in the automotive space. By design, all these families and packages are automotive qualified, most of them up to 125 degrees Celsius. We are optimizing our manufacturing footprint by doing an in-house dual sourcing or sometimes multi-sourcing, both for die and packaging. So we have multiple facilities for dies and packages to ensure a risk-free supply chain. And as I mentioned, we are the leaders to come up with this diamond package, which is the smallest in the industry today.